Morning, everybody. This is Mr. Coker, and welcome back to some more Chapter 16 for AP Chemistry, 16.2 Precipitation and Qualitative Analysis. So this is the second of three sections in Chapter 16. So in this section, we will be talking about the conditions under which a precipitate will form and how precipitation may be used to separate a mixture of ions, particularly cations, metal ions. Most important thing to keep in mind here is that in precipitation, we're talking about the opposite of dissolving. So we've been talking about dissolving process and how KSP, if it's small, means that things aren't very soluble. Now we're turning it around. We're talking about putting ions together and letting them form a solid. That's the opposite of dissolving. So for the equilibrium constant, it's going to be the reciprocal for the dissolving process. So if you've got a small KSP, the precipitation reaction is going to have a large K. In other words, it should go to completion. So putting ions together means you should form a precipitate. If you have small concentrations of your ions and you're not sure if the concentrations are large enough to form a precipitate, all you need to do is calculate the ion product, or what we would call the reaction quotient. Remember, capital Q. Capital Q tells you if an equilibrium will shift to the right or the left. And so if Q is greater than K, SP, that means a precipitate will form. So we think of KSP being the ions multiplied together to make the equilibrium constant KSP. If your ions have a concentration where they are greater than K, it means you have more of the ion than you can have based on the solubility. So the ions will form the ionic solid and go back to the solid step. So in other words, it will shift the equilibrium to the left and form the solid on the left side of the dissolving equation. For calcium fluoride, for instance, the Q would be the ion calcium times the ion fluoride squared. If that product of calcium times fluoride squared turns out to be greater than KSP, then your calcium and fluoride ion mixture should form a precipitate. So if you're, say, for instance, doing calcium fluoride, simply calculate Q, and from Q you can tell if the equilibrium is going to form precipitate. So let's do our first math problem on this. Let's say we have a solution prepared by adding 750 milliliters of 4 times 10 to the minus 3 molar cerium 3 nitrate to 300 milliliters of 2 times 10 to the minus 2 molar potassium iodate. So the precipitate we're wondering if it's going to form is the cerium iodate. Of course it's not the potassium nitrate. Potassium is always soluble, nitrate is always soluble. So it's the cerium iodate that we will be considering. The KSP for cerium iodate is 1.9 times 10 to the minus 10. So that's a small K. So there's a very good chance we might form a precipitate by mixing these ions, but these ions do have low molarities. So first, let's find out what the concentration of each ion is. Now you might be saying, wait, we know the concentrations. 4 times 10 to the minus 3 for cerium, 2 times 10 to the minus 2 for iodate. However, don't forget, mixing them together means the volume of the other solution dilutes the molarity of the concentration of the first solution. So we don't have 4 times 10 to the minus 3 molar cerium nitrate. We need to do an M1V1 equals M2V2 problem on it. We need to find that the molarity 1, 4 times 10 to the minus 3, and the volume 1, 750 milliliters, will equal the molarity 2 after adding the 300 milliliters of the other solution to it, times the volume 2. So just like when we mix solutions to make calibration plots for our spectrophotometry experiments, we need to consider the fact that these two solutions are mixing together and diluting the molarities of each other. Keep that in mind. That's a very important thing on the AP test. realizing that when two solutions are mixed, whether acid and base or acid and water, or in this case two solutions of ions, that their volumes add together and they dilute each other, and you have to do an M1B1 equals M2V2 on it. The only time you don't have to do this is when it tells you that what you're adding is not changing the volume of the solution. For example, if you bubble a gas into a solution, likely that's not going to change the volume. If you add a small amount of solid to a solution, like pellets of NaOH, those aren't considered to change the volume. But adding two solutions together, you know the volumes are going to change, so the molarities are going to change. So I've already worked out the algebra. It's 750 times 4 times 10 minus 3 divided by 1050, 300 plus 750. So the molarity of cerium ion is going to be 2.86 times 10 minus 3 molar. Likewise, doing the same kind of math on the iodate, the molarity of the iodate is going to be 5.71 times 10 minus 3 molar. Now I can plug them in and find the reaction quotient. So it's the cerium times the iodate cubed, because when cerium iodate dissolves, you get 3 iodates and 1 cerium. So when that's calculated, you get 5.3 times 10 minus 10. Now 5.32 times 10 minus 10 is bigger than 1.9 times 10 minus 10. So that means you have more ions than you're allowed to have in an equilibrium mixture. So what are the ions going to do? They're going to form the solid. You're going to form some solid. It's going to settle to the bottom. Precipitation will occur. If QSP is greater than KSP, precipitation occurs. If QSP is less than KSP, then you are unsaturated. If Q equals K, you have a saturated solution and you have an equilibrium. Now notice, precipitation occurs, but not all of the cerium and iodate will precipitate. Some will stay in solution, exactly enough that the cerium times the iodate cubed equals 1.9 times 10 minus 10. In other words, it shifts to the left, but only as far as it takes to get back to equilibrium. Okay, a more complicated problem would be finding how much you have after the precipitation. So I just alluded to it in the last slide. What if you want to know the concentration of each ion after the precipitation occurs? So let's try one of these. 100 milliliters of 0.05 molar lead-2 nitrate mixed with 200 milliliters of 0.1 molar sodium iodide. Of course, we know it's not the nitrate and we know it's not the sodium. It's going to be the lead-2 iodide that's going to precipitate. So lead-2 iodide has a KSP of 1.4 times 10 minus 8. What we want to know is what is the molarity of lead plus 2 and I minus 1 after the precipitation occurs. So we're going to start by finding the initial molarities of each ion. So just like we did in the last, take the volume 1 and the molarity 1, divide by the volume 2, and the volume 2 is going to be the sum of the 2 milliliters, 100 plus 200 milliliters of the two solutions, because each one's new volume is the total volume of the mixture of the solution. That gives us 1.67 times 10 minus 2 molar for the lead-2 and 6.67 times 10 minus 2 molar for the iodide. Now, plugging it into Q, we get that the Q is 7.43 times 10 minus 5th, which is greater than 1.4 times 10 minus 8. In fact, it's a lot greater. So we know a precipitate is going to form. Now, here's where the technique comes in. K is small. So our first assumption is going to be that the precipitation K is going to be large, so we are going to first assume it goes to completion. So this is like adding an acid and base together, and we assume it goes to completion because K is large. Remember that from before break. Now, that goes to completion, but it doesn't mean both ions are used up. The limiting ion will be used up. So to do that, we need to do a little stoichiometry. So molarity is not enough. We're going to need moles. We're going to take 0.1 liters times 0.05 molar for the lead ion, find out we have 0.00500 moles of lead plus 2. We're going to take the 0.2 liters times the 0.1 molar for the iodide, find out we have 0.02 moles of I minus. Now the precipitation reaction is lead plus 2 I minus yields PbI2. Notice I only show the arrow to the right. We're assuming it goes to completion. We have more than double the number of iodides than leads, so we know lead is going to be used up first. So the lead plus 2 goes to 0, and the I minus goes to 0.02 minus 0.005 times 2 iodides for every lead. All the lead's used up, so 0.005 times 2 is 0.01. So we start with 0.02, we use up 0.01, we're going to have 0.01 moles of I minus left over. So what I just described there, if you need to draw it out in more detail, it's just an ECMS problem. Start with the moles of lead plus 2, the limiting reactant, find the moles of iodide used, subtract from what you started with, that's how many moles of I minus are left over. Okay, now that we've assumed the reaction goes to completion, we're going to let the lead iodide solid sitting on the bottom of the container now reach equilibrium. We're actually going to let it redissolve a little bit until it reaches equilibrium. So what we do is we assume we have some PbI2 solid. We know we do. We formed a precipitate. And we let it reach equilibrium with the lead plus 2 and the iodide in solution. Now remember, the lead plus 2 was used up, so our initial molarity of lead plus 2 is 0. However, 0.01 moles of I minus are left over. And it's in 300 milliliters, or 0.3 of a liter. Well, 0.01 moles divided by 0.3 is 0.0333 molar I minus. We don't start with 0 I minus, we start with 0.0333 molar I minus. However, with no lead, we can't shift to the left, so we have to shift to the right. So the change is going to be plus X for lead and plus 2X for I minus. So our equilibrium amount is going to be X for lead plus 2, X for lead plus 2, and 0.0333 plus 2X for I minus. Now we can plug those numbers into the KSP. KSP is 1.4 times 10 minus 8, so that equals X times 0.0333 plus 2X quantity squared. Here's where the shortcut comes in. K is small, so 2X is going to be small compared to 0.033. We neglect it. So now we see that solving for X is just a matter of dividing 1.4 times 10 minus 8, KSP, by 0.03333 squared, and we get 1.3 times 10 minus 6 molar. That is now X, and X is the lead plus 2 at equilibrium. Lead plus 2 at equilibrium is 1.3 times 10 minus 5 molar. I minus at equilibrium, remember we neglected the 2X, is still 0.0333, or 3.33 times 10 minus 2 molar. So to summarize, what you first do is you check to see that a precipitate does in fact form using the Q approach, but where you look to see if Q is greater than K. If it does, you assume that the reaction occurs stoichiometrically, not equilibrium-wise. You assume it goes all the way to the right, using up one of the two ions. So now you do a little ECMS on it. After you've done that, then you go back and do the ice table using the initial amounts of each ion. 0 for the one that was used up, and whatever molarity it is for the one that's left over. Then do the change in the equilibrium, solve for the X, and then go back and figure out what each one is in the equilibrium reaction from the ice table. Okay, just going through another example like that real quick. This is an example in the textbook 16.6. Solutions prepared by mixing 150 milliliters of 1 times 10 minus 2 molar magnesium nitrate and 250 milliliters 1 times 10 minus 1 molar NaF. Calculate the concentrations of magnesium ion NF minus at equilibrium with the solid magnesium fluoride that has precipitated. Magnesium fluoride has a KSP of 6.4 times 10 minus 9. Well, we're first going to check to see the precipitate forms. We find the molarity of the magnesium plus 2 using molarity 1 times volume 1 over volume 2 equals molarity 2. For mixing the two solutions, we get 0.00375. I actually prefer to kind of work in the decimals instead of the scientific notation here. F minus 250 times 1 times 10 minus 1 divided by 400 is 0.0625. Plug them in. Q equals 0.00375 times 0.0625 squared equals 1.46 times 10 minus 5th. Yes, we are going to have a precipitate because that's greater than KSP. Now, we assume the reaction goes to completion. We first calculate the moles of magnesium ion, 0.0015, the moles of fluoride, 0.025, and we look at the balanced equation, Mg plus 2F minus. Well, it's going to be 2 fluorides for every magnesium, but we have a lot more than 2. We have almost 20 times as many fluorides as magnesium, so we have lots of fluoride compared to magnesium. Magnesium is limiting. It goes to 0. The fluoride is going to go from 0.025 to 0.025 minus 2 times 0.0015. So if you work that out, put it down on paper, work it out, you get 0.022 moles of F minus left over. It's in a 400 milliliter solution, so when you divide 0.0220 by 0.4, we get 0.055 molar F minus. So in our ice table, we plug in 0 for the magnesium. It was all used up. We plug in 0.055 for the F minus. Our change is going to be plus X and plus 2X for the F minus, and X and 0.055 plus 2X for the 2 molarities at equilibrium. KSP then is going to be 6.4 times 10 minus 9. Oops, looks like an extra parentheses sign in there. Equals X times 0.0550 plus 2X quantity squared. Neglect the X. Actually, here we're neglecting the 2X. There's another misprint there. Neglect the 2X, and we get X equals 6.4 times 10 minus 9 divided by 0.0550 squared. And that comes out to 2.1 times 10 minus 6. So that means magnesium at equilibrium is going to be 2.1 times 10 minus 6, and the fluoride is going to be 0.0550. That problem was worked exactly like the previous problem with the lead iodide. I noticed some of the problems in the back of the chapter talked about different ways to change the solubility. Of course, we know that adding acid can affect solubility from the previous discussion yesterday in yesterday's YouTube video. However, I didn't really find in the book where it talks about solubility and temperature. Of course, we all know that equilibrium constants K are actually temperature dependent. K can increase or decrease with temperature. Now, for solubility, usually for ionic solids, if you think about all your different ionic solid solubility graphs, solubility goes up as temperature goes up. Or in other words, at higher temperatures, KSP is going to be a bigger number. And as you can see by the graph, this is typical of different compounds, that the KSP will go up with temperature. So if KSP is increasing with temperature, solubility is increasing with temperature. One way to get an ionic solid that's stubbornly not dissolving to dissolve might be to raise the temperature. Now, we're going to look at a practical application. Now, this is probably mostly used in the chem lab, but it's a practical application for dealing with mixtures of metal ions. So typically, the task that a teacher would give students would be, here's a mixture. I want you to tell me what is in this mixture. What metal ions are present in this mixture? Is copper plus 2 in this mixture? Is mercury plus 1 in this mixture? Is lead plus 2 in this mixture? Well, in a mixture of ions, trying to test for each ion can be complicated if you don't separate it out. So to separate that mixture out into individual portions of the mixture, each one with the particular metal in it, we need a technique called selective precipitation. So here what we're using is various anions, And we're using anions, and by that I mean something like chloride or sulfide or sulfate or carbonate. An anion is added that only forms a precipitate with 1 or 2 or maybe 3 metals in the mixture. And that's called selective precipitation. You can have a mixture of a lot of different metal ions, but by using the right anion carefully, you can in fact separate the mixture out as far as by precipitating one of the metals. This might be useful, say, for tap water. Let's say that you have lead in tap water, but by adding a particular ion, you can get the lead to precipitate out, and now your tap water doesn't have that ion in it, the lead ion. Let's take a look at a first example here, just a simple little example of 2 ions, barium and silver. Barium plus 2, silver plus 1. That's an easy one to separate. All you have to do is add a little sodium chloride to the solution. Silver plus 1 and chloride minus 1 is an insoluble combination. It's got a small KSP. Barium chloride is soluble. So adding chloride to a barium and silver ion mixture will precipitate the silver. The silver settles to the bottom. If it's not settling fast enough to suit you, you can put it in a centrifuge and spin it real fast, and it will force the solid to the bottom. Now you've got the solid on bottom. There's your silver, and you've got the solution, which contains your barium ions. You could use a technique of decanting, which is pouring off the liquid to get the barium separate from the silver, or you could maybe take pipettes and pull it off. The liquid you're pulling out of the mixture is called the supernatant, and the solid sitting on the bottom is the precipitate. So if you're not part of the solution, you're part of the precipitate, right? So the solution is here's a little vocab word for you. It's the supernatant. So here is a problem in using some math on selective precipitation. We've got a solution, 1 times 10 minus 4 molar copper plus 1 and 2 times 10 minus 3 molar lead plus 2. We're going to drip in a solution of I minus 1, maybe sodium iodide, and we're going to add it gradually to the solution, just a drop at a time. And what we're wondering is the lead iodide going to precipitate first, or is the copper plus 1 iodide going to precipitate first? We know there are 2 KSP values, 1.4 times 10 minus 8, 5.3 times 10 minus 12. So which one precipitates first? Well, first let's specify the concentration of I minus necessary to begin precipitation of each salt. Now remember, this is a mixture, but it's already been mixed. So the molarities are 1 times 10 minus 4 and 2 times 10 minus 3. So for the lead iodide, the KSP is 1.4 times 10 minus 8, right? So that's going to equal the molarity of the lead plus 2, which has already been told, 0.002 or 2 times 10 minus 3, times the iodide squared, or x squared. So we're trying to figure out what I minus needs to be before precipitation occurs. So in other words, for precipitation to occur, Q needs to be greater than K. So let's first find out what x will make Q equal to K. So 0.0020 times x squared equals 1.4 times 10 minus 8. Solve for x, you get the iodide that will be at equilibrium with lead is 2.6 times 10 minus 3. Likewise, doing the same thing for copper iodide, copper 1 iodide, I get that the iodide is 5.3 times 10 minus 8. So in other words, as I slowly bring up the molarity of iodide, when it reaches 5.3 times 10 minus 8 moles per liter and goes beyond that, the copper plus 1 iodide begins to precipitate. I have to get the iodide up to 2.6 times 10 minus 3 and beyond before the lead will precipitate. So what we've just shown here is that iodide will precipitate copper plus 1 in this mixture before it precipitates the lead plus 2. So we can add the iodide until all the copper plus 1 has been precipitated, and then pour off the supernatant, and the mixture will be separated. Sulfide is a very common example of something that is used to separate metal ions. Metal sulfide salts often have very different solubilities. So that makes sulfide very excellent for selective precipitation. It will precipitate one ion but not another because they have very different solubilities. Let's say we have a mixture of 10 to the minus 3 molar, 0.001 molar iron plus 2 and manganese plus 2. And we add sulfide, S minus 2 to that. Our FeS is going to precipitate first because FeS is less soluble. How do I know it's less soluble? The KSP for FeS is 3.7 times 10 minus 19. The KSP for MnS is 2.3 times 10 minus 13. Since they both form two ions, the FeS is going to precipitate first. Carefully adding S minus 2 is going to precipitate the Fe plus 2, and that's going to leave the manganese plus 2 in the supernatant. Now, S minus 2 is basic, which means we can control how much S minus 2 we have in solution by regulating pH. Remember, H2S makes H plus plus HS minus. Ka1 is 1 times 10 minus 7. And HS minus makes H plus plus S minus 2. And the second step, Ka2, 1 times 10 minus 19. So if you look at these two equilibria, in an acid, S minus 2 is going to be very small, because you add H plus and you're going to shift the equilibrium towards HS minus and then towards H2S. But in a base where you're taking H plus out of solution by reacting with OH minus, there's going to be a lot of S minus 2. So for H2S, if H2S is added as your reactant to precipitate, you can actually control how much S2 minus you have by using acid or base pH. So metal ions that have very small KSP, they're precipitated by using a slightly acidic solution, whereas minus 2 is very small. But then if you slowly make it more basic, you will then begin to precipitate the metals that are have slightly larger KSPs. So for example, FeS might precipitate in a mixture of H2S that has a more acidic pH, but MnS will only precipitate in a more basic pH. So to illustrate that, here we've got Mn plus 2, Ni plus 2, Cu plus 2, and Hg plus 2. So let's say we add H2S and we have a pH of about 2. So that's not going to be very much S minus 2. Copper sulfide and mercury sulfide have very, very tiny KSPs. So they're actually able to precipitate even at that very small amount of S minus 2 that you're going to have at a pH of 2. So at a low pH, you can separate from this mixture of 4 ions, you can separate out the copper and the mercury. Then you can later redissolve them and figure out how to separate the copper from the mercury. What you're going to be left as your supernatant is going to be Mn plus 2 and Ni plus 2. Then by adding hydroxide and bringing your pH back up, you can then get those two to precipitate. So you can see you can get these various mixtures to precipitate selectively. You can separate out the mixtures using careful addition of an ion and then also maybe regulating that ion using pH. Here is a large, complicated example of one of these. I just want to kind of show it to you, not ask you to be able to recreate it. Let's say you've got a mixture of all 21 of these ions here, from mercury 2 all the way up to K plus 1. Well, the first thing you could do is you could precipitate the mercury plus 1 and the silver and the lead using chloride. So you could add HCl and it'll precipitate those three out, and those would be your group 1 ions. Then maybe you would have, you'd take that precipitate and you'd figure out how to separate the mixture from there. That would leave you with your supernatant being groups 2 through 4. Then you would add H2S, and you'd get the mercury plus 2 and the cadmium and the bismuth and the copper plus 2 and the tin to separate out, and those would be your group 2 ions. Now remember, you can get your group 2 ions separate, maybe using pH or something. You could figure out how to get some of those to dissolve while others stay in solution. Well, that's going to leave you with a supernatant with groups 3, 4, and 5. Maybe there you add the NaOH, and you get precipitates of some of the others that are maybe more soluble at a higher pH with sulfide, and maybe some even that precipitate with hydroxide. Your solution of groups 4 and 5 will then be left in solution, and you'll add sodium carbonate to that, and you will precipitate out the calcium carbonate, the barium carbonate, the magnesium carbonate. Those would be your group 4 ions. And your group 5s, which are going to be your ammonium, your sodium, your potassium, are going to still be soluble. Sometimes the only way to find out what group 5 you have is by the flame test. And you might even have to use the cobalt glass to separate whether you have sodium or potassium in your flame test. So you can see, using a very careful step-by-step process, you can actually analyze a mixture that is a very complicated set of different ions. It's called qualitative analysis. This whole process of determining what ions are in a mixture by using very careful use of solubilities and precipitates, and often if you're good at this technique, you can recognize a precipitate by its color or by its even by its texture, jelly-like, or little crystals, or sparkly, or different little cues can help a person figure out what they actually have. Okay, so that's the section 16.2. Here are some review questions I'd like you to try. Once again, if you look at the question, you say, oh, I know that, move on to the next one. If you look at it and you say, I'm not so sure, go ahead and try it. Remember, the blue ones are in the back of the book, and that will give you some practice on this going into our multiple choice homework that we're going to turn in and the quiz on Friday. I wanted to talk briefly before closing today about the AP test. So I'm not getting a lot of updates from AP. Some of you are actually probably getting updates in more detail than I am, but it appears at this point, don't hold me to this, but it appears at this point that what they're posting on the AP website looks like they're going to be testing over the first 7 units of the AP Chem curriculum. So just to review what the first 7 units are, it's atomic structure and properties, molecular and ionic compound structure and properties, intermolecular forces and properties, chemical reactions, and kinetics, thermodynamics, now that would be delta H, and calorimetry, and equilibrium, unit 7. Now, part of unit 7 is the equilibrium of KSP and solubility. So we're going ahead with this week and using it to wrap up unit 7. Now it appears that I've actually jumped the gun and already talked about acid-base, but it looks like at this point maybe acid-base and pH will not be on the AP test. So what I'm hearing is that you're going to be allowed to take the AP test online. It'll be 45 minutes instead of 3 hours. It'll all be free response. You will work out your answers and somehow submit those answers, even if it's a matter of taking a picture of the piece of paper you wrote your answers on. But at this point, we're going to be waiting for more information, but at this point, that looks like what the AP test is going to be. They're actually going to be flexible about when you take the AP test, thinking that some people may want to take it early while they're still fresh instead of waiting till May. So keep that in mind, but I want to first finish equilibrium, and maybe by next week we'll have a little more clarity and I can begin to make some suggestions to you as to how to wrap things up, do your review, and take your AP tests. So looks at this point like Unit 8, acids and bases, and Unit 9, applications of thermodynamics. That includes thermodynamic favorability, which is the delta S and the delta G stuff that I may have mentioned in class, which we haven't covered yet, but we would have been covering in a later chapter. And then also the electrochem doesn't look like it's going to be on the AP test either. So it looks like we're in pretty good shape as far as being prepared for the AP test. We just need to get the KSP stuff figured out and get our equilibrium figured out. And then we are probably going to start reviewing at this point. Now, where I'm getting some of this information is I was sent on Google Classroom the website where AP students are getting some updates on what to do about the coronavirus. And on that same site, I did notice that they are offering some online lessons. So I just want to highly encourage you to try these out, see if they're any good, maybe give me some feedback. But on Wednesday, March 25th, which is tomorrow, 10 to 10:45 Eastern Time, a.m., that would be 9 to 9:45 Eastern Time for us, they are presenting a lesson 8.1, Introduction to Acids and Bases. Now, I know we've already covered that, so this would be something that you can optionally look at if you want to, but they are going to be offering, I believe, the Unit 8 and Unit 9, maybe not covered on the AP test, but still, if you want the full coverage of what you should have learned this year, it's a chance to see the information presented by, I assume, going to be excellent teachers that AP has handpicked to give these lessons. So just want to highly encourage you, if you want to come out of the year, despite the interruption we've had, if you want to come out through the end of the year with a very good understanding of the material from AP Chem, going into college, taking it in college, you want to make sure that you don't miss out on any of the information. I encourage you, watch these little videos. I assume that's what it's going to be, some kind of video online lesson that they're going to give you. It might be PDF, but whatever it is, I encourage you to go ahead and get at those. Just remember that the stuff in Unit 8 is actually stuff we have covered in class. So that would probably be less important. When they get up to covering the Unit 9 stuff, I would very highly encourage you guys to take a look at that. So if you're not sure if you understand acid-base, go ahead and look at these topics that they're offering, AP is offering to teach you, and maybe give me some feedback on Google Classroom. Hey, I watched it, it was terrible, or hey, I watched it, it was great. And then we can encourage our other AP students in the class to maybe take advantage of this resource. I would say it's a resource. AP is offering it for free to AP students. Go ahead and take advantage of that. A lot of the stuff I'm telling you about AP Chem probably also fits with your other AP classes as well. All right, so that should wrap us up for today. And just keep in mind that I will be continuing to post lessons as long as I think I can help you get ready for the AP test. Take care. Goodbye.